Okay, so I want us to look at how do we go about balancing a redox equation. But before we do that, I want to point to a simple example of a redox reaction here, just to illustrate some very important concepts and principles that will apply when it comes to balancing redox equations. Now, what we have here, what this picture is showing you, is what happens when you put a coil of magnesium in a solution containing copper 2 sulfate, right? And what you'll observe, if you put the magnesium in the copper 2 sulfate, you'll notice first that the copper 2 sulfate is blue in color, right? So if you put the magnesium in the copper 2 sulfate and you wait a while, then what will happen is that you're going to see the blue color start fading until it becomes colorless. In addition, you're going to see some material deposited on what is left of the magnesium. And it turns out that that substance is actually copper. All right. So a reaction is taking place where the magnesium metal is reacting with the copper 2 sulfate to form products where copper is deposited and the solution is cleared up. All right. So I'm going to write down the equation. Let me get out of this here. And I'm going to, okay, let me go here. I'm going to write down the equation for the reaction that is actually taking place. Okay, you know what? Let me do that down here. Okay, so the reaction is the magnesium solid is reacting with the copper 2 sulfate, which is in an aqueous solution, to form. And what will happen is that the magnesium is going to displace the copper. So you're going to end up with magnesium sulfate aqueous. And the substance that is deposited, as I said before, is the copper, which would be a solid, right? Now remember, this is blue in color. So eventually all the copper 2 sulfate will be used up and the blue color will disappear. And this here is colorless, right? So that's the reason why we observe the transformation from blue to colorless for the liquid, for the solution. Okay, this would be the molecular equation. Again, the molecular terminology is a bit misleading because there are no molecules present, but that's a terminology that is used. Okay, so we can go from the molecular to the ionic equation, right? And in this case, the magnesium solid would be unchanged. The copper 2 sulfate would be in an aqueous solution, so that will dissociate to form Cu2 plus aqueous and the SO42 minus aqueous. All right? And then on this side, the magnesium sulfate, that would also be dissociated to form Mg2 plus aqueous and the SO42 minus aqueous. All right? Plus Cu solid. All right? So to get to the net ionic equation, net ionic, what's going to happen is the sulfate here and here will cancel out. So you'll be left with Mg solid plus Cu2 plus to give Mg2 plus Cu. And this would be the net ionic equation, right? Now, a couple of things I want to point out here. You'll notice that as far as the magnesium is concerned, the oxidation number of magnesium here is 0, and here it's +2, all right? So there's a change in oxidation number from 0 to +2 for the magnesium, and that's because as you go from magnesium to magnesium ion, you're losing 2 electrons, all right? So therefore, because electrons are being lost, the magnesium is said to undergo oxidation. All right? And then as you go from Cu2 plus to Cu, the change in the oxidation would be from +2 to 0. All right? So in this case here, the copper 2 plus would be gaining 2 electrons, and the result, or we call this reduction as a result. All right? So basically, that's what happens as you go from copper 2 plus to copper. All right. So that's what we have here as far as the oxidation reduction reaction taking place between the magnesium and the copper 2 plus. All right. So that's what happens. What you're observing here is what happens in every redox reaction, right? Basically, one substance would be oxidized by losing electrons, and the other substance would be reduced by gaining electrons. Another thing I want to point out here, and this is true again for every redox reaction, whatever the number of electrons that is gained by one substance is equal to the number of electrons that is lost by another substance. All right? That is true for every single redox reaction. And you're going to see this when we start looking at balancing redox equations. All right? So I just thought I should show you this particular example so that you understand the underlying principles taking place in any and every redox reaction. Okay, so what I'm going to do is I'm going to go back to this slide here to look at a specific example. And this is a typical question you could be asked. How do you balance a particular redox equation, right? So in this case here, we're looking at the oxidation of iron 2 plus to Fe3 plus to form bidichromate ion in an acid solution. So the first step involved is that we need to write the unbalanced equation for the reaction in ionic form. And this would be the unbalanced equation right here. The Fe2 plus is reacting with the dichromate to form the Fe3 plus and the Cr3 plus ion, all right? In some cases, you might be just given this to begin with, and therefore you need to move on to the next step. So what's the next step? The next step is that you separate this equation, this unbalanced equation, into two half equations. So the first half would be the oxidation, which would be the conversion of the Fe2 plus to the Fe3 plus. The second half would be the reduction, where you convert the dichromate ion to the chromium 3 plus ion. All right? Okay, the third step is where you balance all atoms other than oxygen and hydrogen in each half equation, right? So in the case of the first half equation, there's no change needed because the iron here is 1 on 1 on both sides. However, in the case of the dichromate, you have two chromium atoms on the left and you have one on the right. So therefore, to balance a chromium on the right, you put 2 here in front of the chromium ion on the right, and now the chromiums are balanced, right? So that's basically what you do in the third step. You basically balance all atoms apart from oxygen and hydrogen in each half equation. The next step is that for reactions in acid, you're going to add water to balance the oxygens, and you're going to add H plus ions to balance the hydrogen atoms, all right? So in this case here, you have 7 oxygen atoms on the left, right? So we need to add 7 water molecules to the right, because by adding 7 water molecules, you're adding 7 oxygen atoms on the right, which balances with the 7 oxygen atoms on the left. In the case of the other half reaction, there's nothing needed to be done because there's no oxygens present. Okay, so the next step is that we balance the hydrogen ions by adding, or I should say we balance the hydrogen atoms by adding hydrogen ions. And that means that in this case here, where you have 14 hydrogen atoms on the right, you need to add 14 hydrogen ions on the left, all right? So that's how we balance the oxygens and the hydrogens. We balance the oxygens by adding water to the side that needs it, and we balance the hydrogens by adding the H plus ions to the side that needs it. Then we get to the next step where students tend to mess up a whole lot, but you have to be careful when doing this. So let me explain how you tackle this part. So not only do we need to balance all the atoms, but we need to make sure that the total charges on the left is equal to the total amount of charges on the right. And the way we do that is that we add electrons to one side in order to achieve that balance. So in the case of the first half equation here, where we have a total of +2 here on the left side, we have a total of +2 here on the left side and +3 on the right side. To balance the charges, we add 1 electron here, because by adding the 1 electron on the right side, we reduce the charges on the left by 1. So the total charges here would be equal to +2, which balances with the +2 on the left. In the case of the second half equation, if you add up the charges on this side, on the right side, this would be +6, And before you add the electrons to the left side, this is going to be plus 12, right? So what we need to do is add 6 electrons to the left side so that the total charges as a result of the addition of the 6 electrons will be 12 minus 6. That gives you plus 6, which balances with the plus 6 on the right side. All right? So that's basically how we balance the charges. We balance the charges by adding electrons to one side so that the charges balance out, right? The total number of charges on either side will be the same. And then the next step is, let me erase what I wrote here so that you can read this more clearly. Okay, so the next step is where, whoops, let me go back to pointer. Okay, so the next step is where, and if you remember, we said that in any redox reactions, the number of electrons transferred or lost and gained must be the same. Well, you'll notice here we have 1 electron here, we have 6 electrons here, so they're obviously not the same. So what we need to do to achieve similarity between the number of electrons lost and gained here, we need to make sure that we multiply the half reactions by the appropriate coefficients so that the number of electrons lost and gained would be the same. So what that means in this case is that we need to multiply this half equation here by 6, right? So that we end up with this. And therefore, as a result, we can now add these two equations together, which would be the next step. But you'll notice here that we have 6 electrons. I'm sorry. You notice here we have 6 electrons here and 6 electrons here. So therefore, when we add them together, this is what happens, right? The electrons will cancel out because the number of electrons lost and gained will be the same, and there's nothing else to be canceled out, and therefore we simply write down what is left, and that would be the final answer in terms of the balanced equation. However, let me just say this, that I would recommend that you would check to make sure that this is balanced. So you should do basically a check through to make sure that you have the same number of atoms of each element on both sides, as well as the charges being balanced as well. So if you check this out, you'll see that you have 14 hydrogens here, 7 times 2, 14 hydrogens. So the hydrogens are okay. You have 2 chromiums here. You have 2 chromiums here, so that's okay. We have 7 oxygens here, 7 oxygens here, that's okay. And then finally, we have 6 iron here, 6 irons here, that's okay. And then we have to look at the charges, right? We have to make sure that the total number of charges on the left is equal to the total number of charges on the right. And that's what this calculation here is showing you. So for this side here, you have 14 plus charges minus 2 plus 12. So that's what's being shown here, and that gives you 24. And 6 times plus 3, that's 18, times, or added to 2 times 3, 6. So that's 18 plus 6, 24. So the charges are balanced as well. So now we are confident that this here is the final answer as to being the balanced redox equation for this reaction. All right? Okay, so that's basically how we go through stepwise to determine the balanced redox equation based on previous unbalanced equation. All right, so that's it for now. The next video I'll post up will give some more examples of balancing redox equations. Until next time.